Yeah, welcome. I'm Christian van Zorn from RWTH Aachen University in Germany, and together with my colleagues, we had a look at how we can detect ransomware in real time despite the overhead that is caused by behavior monitoring of I/O behavior. So, if you have heard, even in today's times, according to recent security reports, ransomware is still the second biggest threat to cybersecurity, even though we're doing a lot of research to try to prevent ransomware attacks in the future. A great example we have already heard yesterday in the keynote, the Colonial Pipeline attack from 2021, in which ransomware caused a 6-day shutdown of this pipeline that led to widespread fuel shortages across the southeast of the US. In our talk, we primarily focus on cryptographic ransomware, that is ransomware that encrypts the user's files to prevent the user to access these files, and then demands a ransom to release the keys for the user to be able to access the files again. So how does ransomware detection in this case typically work? Well, all ransomware is typically in common that it requires disk access to actually perform its task. To first find which files to encrypt and then finally to encrypt them. And we can exploit that by using, for example, the access patterns, how files are accessed, the fact that ransomware typically targets user files, so documents or images, and tries to capture all of these, which is a different behavior than what we see by benign software. So how does now monitoring overhead come into that? Well, this behavior detection has already been around since 2016. For example, the Continella et al. Published their ShieldFS paper where they presented a self-healing file system, and they found that simply creating a backup of a file when it's written to, that can already create an overhead of 3.8 times. However, they also performed real-world measurements, and in these measurements they found that this overhead apparently was not that much noticeable to real-world users. And when looking into that and also other research, we found that it probably was caused by the fact that they use hard disk drives, which are inherently slow. So the overhead due to the I/O is not really that noticeable. But today we have typically SSDs, which are much faster and have a much higher IOPS count. So we expect that this overhead is much more noticeable today. So since then, research has primarily focused on improving detection and also the overhead of the machine learning approach itself. But apparently, the monitoring overhead that actually you need to get the features to then perform your detection has largely been overlooked. And when performing initial experiments, we found that simply enabling the same monitoring that related work does degrades the performance of a SSD by roughly 75%. So basically, the sustained read and write performance of the SSD more closely resembles that of a traditional hard disk drive. So we asked the question, what is actually the cause for this overhead and how can we reduce that? And how does feature monitoring actually impact the I/O overhead? I will give a quick background on how the I/O stack typically works. In generally, applications cannot directly access the hardware and the files. Instead, they use APIs provided by the operating system to perform this access. And that's typically where then security monitoring takes place. For example, on Linux, you can use eBPF to hook into the virtual file system, or on Windows, you can use mini filters to add additional code into the I/O stack to then perform your monitoring. However, at the same time, we see that OS developers are heavily working on improving the I/O stack and increasing its efficiency to make use of modern high-speed SSDs. So we have there kind of conflict of interest between security research and OS developers trying to fully utilize hardware. So we did some measurements to further quantify how this overhead comes to be. And we first checked what happens if you simply install a driver that simply returns, so we do not monitor any features, and we found that just adding the driver is not the cause of the overhead. Instead, once you start recording actual features and parsing this call, for example, giving you the information on which process actually performed the I/O operation, you are already seeing an increase in the execution times for different system calls. If you then get additional features like to resolve the file name of the file that was accessed, or for read and write operations calculate the entropy in the kernel, then this overhead is increasing more and more. So we see on the one hand, some features are actually easy to calculate. On the other hand, we see the more and more features we monitor, the more increase the overhead and the slower the I/O system will actually finally then become. So to solve this, we proposed a multi-staged approach, since in generally you can say that most processes running on a system are benign. So why not only monitor what is required? So on the right, you see an example where we have a linear stage model, where in stage 0, we reduce the amount of features to such a low degree that we have relatively low overhead, while in stage n, we have a lot of features, so we have the scrutiny to actually decide whether the current process behavior is a ransomware and then potentially create an alarm, and based on the process behavior, then want to monitor to move the process between the stages. So for example, here we have a process that performs a write operation, and at this point it's in stage n-1, so we monitor this call, so we actually perform the monitoring, then forward the information to the preprocessing of these features, then we query our stage to make a decision on the current process behavior, and here we see that in this case the process apparently was behaving benign, so that when the next write operation comes in the lower stage, the write operation would potentially not be monitored, and we have a reduced overhead. However, just creating a simple stage model is not really the answer, because we do not yet know how to actually connect these stages properly and what the effects are depending on the different stage designs. And we still do not know really if this dynamic monitoring can actually improve the I/O behavior while still maintaining the detection capabilities of ransomware. So for the stage design considerations, we have basically 3 properties we need to have a look at. First, the classification performance, since we want high recall across all stages to be actually able to detect the ransomware. However, due to the stage model, we have the advantage that we do not need that much of precision in lower stages, since a false positive only results in a higher overhead, but not directly in a false alarm. Then the classification frequency, if we disable the monitoring of a call, we cannot really see any I/O behavior anymore, so it's difficult to trigger when the next decision by our stage model will take place. And finally, the detection latency, so basically the more stages you have, the longer it will take until the ransomware is detected and the more damage it can cause. So we need to have a look at the critical path that the ransomware has from starting its execution to then finally an alarm being raised. So we envisioned 4 different stage designs, where you already saw the naive monitoring approach, but we also considered what happens if we simply skip stages or if processes start in a higher state of scrutiny, and check what effects we will have on detection performance and on I/O overhead. So to judge this, we used the ShieldFS dataset as a basis, because there we have real-world data of real users, so we have a real representation of I/O behavior to monitor overhead and also false positives. And here we see that even with the naive monitoring, where the ransomware starts in the lowest stage, so it has the least amount of features, we are still able to advance the ransomware to a higher stage, and it's finally then being detected. Also, we see that even if we start in an already high stage, so with a lot of overhead, we do not have the problem that we create a lot of false positives compared to a traditional approach. So we see that in general, this approach for 3 or for 5 stages, for example, does work from a detection performance kind of view. To further evaluate this, we also use the models from the dataset that were trained on the dataset to check whether this multi-stage approach is actually also able to detect novel ransomware from 2020 to 2023. And here we found that the simple multi-stage model, which was not modified, is already able to detect 12 out of 47 samples, while also a single-stage approach was not able to outperform this model given the relatively old initial training data. When manually adjusting the hyperparameter slightly, we were able to improve this detection, leading us to the conclusion that the multi-stage approach is not the primary cause for the detection performance. Instead, it's the fact that we had to use the I/O models for the machine learning models with the I/O behavior from 2016. But the multi-stage approach in general does work, at least from a detection perspective. So regarding the I/O overhead, we see that if we monitor all features at the same time that we considered in our paper, we already have an average overhead on benign processes of 180%. If we exclude entropy, which we shouldn't actually do because it's an important feature, we would reduce this overhead to 35%, but still the overhead is quite high. And we cannot really make this decision that we exclude entropy completely due to its importance in feature detection. However, what we saw when looking at the simulations was that benign processes in general, regardless on which stage they start, are quickly moved to a stage with a low overhead, while ransomware processes are quickly advanced to a stage with much scrutiny, so we can make an informed decision. And doing so, we were able to decrease the average overhead on benign processes by 1 order of magnitude, even if we start all processes in a stage with the maximum number of features. And if we would relax this assumption, so processes start in a stage where less features are monitored, we would be able to decrease this overhead even further. So to conclude, we've seen that modern ransomware detection, while providing great results in detection performance, had still the problem that it interferes significantly with IO stacks. So especially on modern systems, we see a great negative impact on the IO performance of modern systems. However, to detect ransomware, it's not necessarily to monitor everything all the time. Instead, by using intelligent monitoring, we can adjust the overhead on a per process level, leading us to a detection performance that is on par with a single stage model, while still reducing the overhead significantly, and thus bringing us further to forward to real-time ransomware detection. Thank you for your attention, and we have also our artifacts, which were evaluated, and you can see them here. Thank you.
Thank you. Any questions? Please, I didn't prepare any questions.
Yeah.
I want to ask you, how did you evaluate the IO overhead?
We use the dataset because using the dataset we could generate a baseline, so we knew what was the overhead if you do not perform any monitoring at all. So we got a baseline of the time the IO execution would take on a modern system, and then we could.
I noticed that you evaluated the IO overhead by utilizing execution time. So is it the time of some benchmarks such as Phoenix or?
No, we used basically these measurements
yes.
over here. So here we had several thousand calls and measured the actual execution time with given different background tasks of these IO operations on the system. First with no driver at all, so that was our baseline on what could potentially be achieved. And then we checked, depending on various feature combinations, how this overhead would increase on the same system given the slowdown of the IO stack.
Oh, okay. Thank you very much.
Hi. My question is on how you see this being deployed. So would this be something you'd have to run in a VM? And this seems like it was run on bare metal. How do you think that impacts?
I mean, the problem with, or the disadvantage of such a multi-stage approach is potentially the detection latency. So you might have already damage that can be caused by ransomware before it's being detected. So we found that in our measurements, this damage was low given we start with suspicious monitoring. So the ransomware would be able to encrypt roughly 3 megabytes of data before it was being detected by our model. But yeah, the idea is basically that currently we often cannot deploy such systems due to the overhead. So that could be an advantage, that we have at least some monitoring and some detection capabilities. Doing it in a virtualized environment would probably be interesting. However, then you get cross effects due to virtualization on the overhead. So I wouldn't be sure how that directly affects the actual IO performance. So if these improvements would still hold due to the overhead that is caused by virtualization, would potentially be much higher than what would be caused from monitoring these features in kernel. So for the artifacts evaluation, for example, we used a virtual machine, and there we found that while still seeing the increase in overhead, it was widely different to a bare metal approach, because the virtualization basically changes the results in these measurements.
Thank you.
Thank you very much, Christian. Great work.